Hello and welcome everybody to week 8. As I promised in the beginning of this course, we will now focus in this last week mostly on recent research results, mostly coming from our group here. So we are very excited now to share these slides with you, and we hope that you enjoy this last week. And our first topic in this video is a system for visual navigation for the Parrot Ardrone. We made this one fully available as open source, so for those of you who have a Parrot Ardrone, and I know that there are some of you around, you can actually try this out at home or in your lab to better see how this works and to have fun with it, and possibly, of course, to extend it. So as you know, the Parrot Ardrone is a relatively low-cost platform. It only costs $300 US, so it's relatively cheap to buy. But a pretty cool thing, and this is what makes it so attractive for us, both in terms of research but also in education, is that it is controllable via Wi-Fi. So the only thing that you need is a laptop, and then you can connect over wireless to the Parrot Ardrone, and it will stream the sensor data, and you can stream back control commands. And the good thing is that the manufacturer decided to put everything, the API and the communication protocols, as open source. So it's very easy to access the data and to control it from a PC. And there are many different language bindings around. For us, we mostly develop in C and C++. This is also the primary library that Parrot is providing. But the community has released other bindings, for example, to Python, and a complete re-implementation in JavaScript running in a web browser. And this has fostered many different directions for research, and also so in our lab we started now roughly 3 years ago with Parrot Ardrones. Now, when you start programming a robot, and Parrot Ardrone is of course also kind of a robot, you need to set up a certain software architecture, in particular when your software solution becomes more and more complex. And most of the time, I guess you've already noticed that a large system then typically consists of multiple components. You have state estimation, you have control at different layers. And for all of that, you'd like to write independent modules that you can link together as you need it for your application. And this is now where so-called robot architectures or software architectures come in. A good robot architecture, of course, is modular, because this allows you to reuse code that you have written before. It is robust, which means that even if one of the components crashes, that it doesn't kill the whole robot. Ideally, if one thing crashes, then it could either be restarted, reinitialized, or just switched off. This also means that you have some tools to know whether something has crashed, to inspect the state of your current system. In particular, with the Parrot Ardrone, you typically have the quadrotor itself in the air, but you also have a base station, potentially other quadrotors at the same time. So a good robot architecture should be decentralized, such that you can add more and more nodes, and that you rely as little as possible on a centralized architecture. As I said before, the modular principle, of course, also facilitates software reuse. You'd like to separate out as many independent libraries as possible to make it as simple to put together as possible. A good architecture also needs to talk to the hardware, of course, so you need some abstraction of the hardware and underlying software libraries to provide a common interface that you can switch one localization module with another one. And this means that you need that it's an advantage to define for certain common modules a fixed interface or a fixed protocol of what information to exchange. Another very important aspect is, because the software won't run from the first day on, so you need to debug it somehow, and that means that if you have an architecture that helps you with introspection, for example, where you can look at where you can switch on debugging output as you go, or where you can look at whether the individual modules are still running and how they are performing, then this greatly helps you. Similarly, it helps a lot if you can log your data to a file and then replay it, just to trace down some of the bugs. This can help. But of course, in the end, you always have to run everything on the real robot, just make sure that it really works. Another aspect, and that's often overlooked, is of course that a good robot middleware should also be very easy to learn and easy to extend. This means, in particular, because we have, at least here now at university, we have lots of new students coming in every semester, and robot architectures that are very hard to understand because they are poorly documented or because there are no tutorials are really, really difficult for students to learn. So a good architecture, facilitates that and has some auto documentation that continuously that makes it easy to navigate within it. Good. And such robot architectures are then also called robotic middlewares. They provide the infrastructure between different modules. They regulate the communication between these modules and provide such data logging facilities. Some of these middlewares, or probably all of them, also help you with, as I said, with debugging. And then an important part is actually visualization of your data, in particular because you will be often debugging things in 3D, and rotation matrices are very hard to read, as you know. It's important that you have tools that simplify visualization of 3D geometry. For example, tools that can directly display transformations or trajectories and so on, and coordinate systems. There are several such systems available. There are some open source ones and some closed source ones. ROS, which is the abbreviation for Robot Operating System, is certainly at the moment the most popular one, so this is what we are using. But there are other systems as well that have quite some popularity still. Player Stage, for example. Carmen has been around for a long time. And YARP and Orocos are also good systems. Orocos is in particular specialized on real-time control. So if you have hard real-time constraints, then probably Orocos is a good thing to look at. And of course there are also all kinds of closed source solutions. They generally have a better support and maintenance, but they also cost money, and it's sometimes hard then to know what some of the modules do internally. So this is just an example to show you how such an architecture could look like for a navigation task. Of course, there is somewhere the robot at the very bottom to which we need to talk to, and then there is typically a set of hardware drivers that gives us access to the raw data from motors or from our sensors. Then typically there is an abstraction layer that just gives us images in general. This is then, for example, provided by ROS, that provides you a common message format for images and transformations. And then on top of that you have all kinds of custom modules, for example, that run localization or visual odometry, that do global path planning. You might have a user interface. And then at the end you need controllers and potentially collision avoidance, subroutines and so on. Good. So this is the website for ROS. It's, as I said, ROS is one of the really good documented systems. So if you're interested in going any further with quadrotors or with robotics in general, then please have a look at ROS. There are very good tutorials, both video tutorials, but also written tutorials with very easy copy and paste code that you can quickly run to understand the basic concepts. And and the whole thing is completely open to the community, so it's very easy to extend and ask for help there. And now let's look at how to actually implement camera-based navigation with the Parrot Ardrone. The following slides now are summarizing our work that we presented at IROS 2012, and of which we recently published a much larger article in the Rust journal just this year. So this is the general picture. We have the quadrotor, as you know, that talks over wireless with our computer, and there we receive images at 18 Hz, sometimes at 20 Hz, depending on the Wi-Fi connection. We also get IMU data from the quadrotor at a much higher rate, and we send back control commands. We chose to send them at 100 Hz, to publish them at 100 Hz, but sometimes you'd like also to reduce this value. And then on the laptop side, we have three parts. We have a Monocular SLAM system that essentially runs our localization. Then we have an extended Kalman filter that fuses this visual localization with our IMU data. And a PID controller that then generates the control commands that we need for position control and waypoint following. So let's first zoom into this Monocular SLAM system. For that, we actually relied on an external library that is also available as open source. It's the so-called PTAM library, Parallel Tracking and Mapping of Klein and Murray, which was published at ISMOR 2007. And it's a so-called visual SLAM system. SLAM stands for Simultaneous Localization and Mapping, which means that we don't assume at all that we are given any prior map of the environment, but that the SLAM algorithm has to bootstrap both the map and has to find its position within this map. So because there is a dependency of localization on mapping, and mapping again depends on good camera poses, this is also sometimes called a chicken and egg problem. The general idea behind this PTAM library is now to extract visual features in the images and then to match these visual features between the keyframes. I don't want to go too much into the detail here. We added some references on edX for a longer explanation of PTAM and SLAM in general. But for the moment, just assume that with this system we are able to optimize. We can use PTAM to estimate the camera poses by at the same time simultaneously estimating 3D feature points in the world. And the cool thing about this PTAM library is that it is highly efficient and available as open source. So it's just a plug-and-play module that we can use whenever you have a monocular single camera to generate a map, a sparse feature map, but a map, and to localize your camera with respect to that in real time. And this PTAM is in principle split into two processes. There is one part that estimates the camera pose in more or less hard real time, and the second thread that does not run in real time and that optimizes the map. And the map optimization problem gets more and more complicated the more keyframes you're adding. So while initially this process also runs in real time, as soon as you add more and more keyframes and features, it gets slower and slower. Good. These two images just give you a quick feeling for how this looks like. We have the video feed from the quadrotor as visualized on the left side. It detects corners in it, so-called fast corners, and then it tracks, like the KLT tracker, it tracks these features through the images, through the video stream, and tries to estimate the 3D position of these features and the camera poses. And this is visualized in here on the right in this three-dimensional, or here in the middle, in this three-dimensional view. You can see the 3D point features just depicted in red, and the camera poses depicted in as coordinate systems further on the left. And then we extended PTAM in two ways. First, we linked PTAM with the Kalman filter that integrates also the information from IMU and simplifies then the recovery, the post-recovery, once the tracking is lost in PTAM. And we also added a scale estimation method that allows us to get absolute scale for a monocular map. And the problem there is that generally if your only sensor is a camera, then you never know how large your world is. Because it could be, camera motions could be very small and then the world could be very small, or camera motions could be relatively large and then the world could be very large. But just from a monocular camera, you can't tell about the absolute scale of the world. But because we have this IMU data, in particular the ultrasound measurements to the floor, we have an absolute measurement, and that allows us then to estimate the scale of the monocular map as well. Good. This Kalman filter then in the middle is just as you know it. The only difference is that it has a slightly larger state vector. We track the 3D position, the 3D velocities, the attitude, the 3DOF attitude, and the yaw speed in its state. And then instead of having a very simple delay-free model, we calibrated our motion model more carefully, so we know exactly how our controls influence the attitude, and then how the attitude influences the speed, and that again the position, and that gives us a much better prediction than what we had now before. The other very important part is that the Kalman filter also allows us to compensate for the delays. We've looked at that in lecture 4, I think, using the Smith predictor. So the idea is that you just run prediction steps of the Kalman filter to predict a little bit into the future, and then to to pass this pose in the future on to the PID controller that then virtually runs without delay. This is now a visualization of this time delay problem. In contrast to what we looked at in lecture 4, we have actually 3 different sources of information, and all of them have different time delays. So the problem here is that the PTAM pose comes in with the largest delay just because we need to transfer the images, and then we need to run PTAM on this image, and this means that we generally have more than 100 milliseconds time delay between the PTAM pose and our current point in time. We're getting also the IMU readings, and those come at two different delays, as Jakob actually found out, and we're modeling this properly. And then we have a Kalman filter that does updates every 5 milliseconds or so. And the thing is now, whenever we get a new observation, we have to roll back the whole EKF. So we store the full state of the EKF for 1 second or so. And whenever a new measurement comes in, we roll back the state and then integrate the measurements again and make a prediction slightly into the future. And the reason for that is that even if we would estimate our state at the last point where we received the last observation, then our pose prediction would still be late, and we would have this delay in the PID controller. And so what we do is we extrapolate our pose roughly 75 milliseconds into the future, just to accommodate for the transmission delays from Wi-Fi and the time it takes for the quadrotor to actually respond. And then on the PID side or the controller side, we just run a very simple plain vanilla PID controller. The set point that we give to the PID controller is a position in 3D and a yaw angle. And then Jakob implemented some high-level control routines to either hover at a particular position, desired position, or that you can run in assisted control mode, where you have a Cartesian joystick, so to speak, that allows you to move the quadrotor in world coordinates instead of in local coordinates, and you can follow waypoints. And this looks now as follows. This is a video that we took at the Open Day in 2011. Here the quadrotor is in the middle of the air. It has a set point that it tries to maintain, and Jakob is continuously pushing it away. And as you can see, the quadrotor realizes that by returning always to its original pose. And this is a quite robust demo. So first of all, you can run it, as I said, also at home or in your lab. But it's also a nice thing to show to people, and you can then show on the computer screen how the raw data looks like of the quadrotor. And this is now visualized a little bit in more detail here in the second video. So first, of course, we can hold a position that is here indicated with this red cross. And then you can see now in the bottom left the 3D map with the camera poses of the keyframes and the 3D visual features. And on the right side, you see the live view from the quadrotor. You can see the features that it found in the world and the features that it successfully matched with world points in 3D and that it uses to estimate its pose. And you can see that the quadrotor is even then able to return to its hovering point when you occlude all sensors for a little while. So in this case, the odometry doesn't give you any useful information. You're completely lost in principle. But because PTAM has a relocalization ability, it can recover then, at least if it looks into the right direction of a known of the scene. But it can even then recover if this is not the case, because we still have the gyroscopes from the IMU that tell us in which direction we're looking at. So in this video, you can now see how the map is actually initialized in the very beginning. So the map is completely empty. The quadrotor takes off, and while it takes off, it initializes these key points, actually using a KLT tracker. And once it has an initialized map, it continuously extends it with new keyframes and new key points. And you can see that you can fly arbitrary figures. This is also one of the basic functionalities. There is even a small scripting language that allows you to fly arbitrary figures with the Ardrone. Yeah, and the cool thing is, because we know the scale of the world, this house or this figure here really has absolute scale. So we can define beforehand how many meters we want the quadrotor to fly to the left or to the right. Good. So to summarize this video, I've shown you now some of our research on the Parrot A Ardrone. We've introduced ROS as a really good middleware that I would recommend you to use. I've introduced briefly PTAM as a Monocular SLAM module that you can just use out of the box. We didn't go much into the details here. As I said, there will be some links after this video to get more information about PTAM if you're interested. And then we showed this working system that enabled visual navigation with the Parrot A Ardrone. It can fly relatively fast and accurate to given waypoints. And as I said, there is full source code and documentation available on ros.org.